characteristic you're going to measure. Why do they call the characteristic that you're going to measure the random variable? They call it a random variable.
Because it's random?
No.
Because it's like individual.
The idea is that when you go ahead and do probability calculations based on this variable, if you go in and make a selection from the population, you do it randomly. But the first thing that you have to do is you have to establish a domain for your random variable. That is to say, if you're talking about tree heights, right? Once you've gone ahead and you've measured the heights of all of the trees around the school, you can find the minimum tree height, the maximum tree height, right? And in the case of distributions that we're going to deal with first, so first we'll deal with discrete probability distributions. Your domain will be finite. What do I mean by that? Your domain will be finite. What does the word finite mean?
Oh, limited.
Limited, yeah. We're going to start with discrete probability distribution, so that means your domain will be limited. So in the context of this thing with measuring tree heights around Mackenzie, what does it mean that the domain of the random variable x, which will be tree heights, will be limited?
You're not measuring every single tree.
You are. But let's say there are 1,000 trees, right? What is the maximum size of your domain in terms of unique values of x that can exist?
The highest value of a tree?
No, what is the maximum number? What is the maximum size of your domain? 1,000, right? Every tree has a different height, right? If your population is 1,000 and every tree has a different height, then your value of x has 1,000 options, right? Of course, if one of the heights is 150 centimeters, let's say.
That's the range, right?
You can call it range domain in this case. We're dealing with one variable statistics right now, so you can call it whatever you want. I'll call it domain because typically we associate, no, I like to call it domain because the probability is going to be dependent upon the random variable x, and typically we associate the letter x with domain, so let's call it domain. Now if you have, let's say you had 1,000 trees, but two of the trees were the exact same height. They were each 150 centimeters tall, okay? Or 150.25 centimeters tall. How many values for your domain would you have? But all the other trees were different. No? 999.
Why? There's still two different physical objects.
There are going to be two trees which are the exact same height, right?
But they are different.
They're different physical objects, but the random variable x that I said we are caring about in this particular scenario I just made up is tree height. So for the random variable x, if it's defined as tree height of a tree on the grounds of Mackenzie, we've now said that two of the 1,000 trees have the exact same height. Therefore, your domain only has 999 unique values now. Because let's say trees 1 and 2 have the same height, right? And the remaining trees are all different and they have unique values. So in that particular case, we would say that the frequency of trees with a height of 150.25 centimeters would be 2, correct? And the frequency of all other trees would be 1, right? Now to turn that into a probability, of course, you would simply take the frequency associated with each random variable and divide it by the total number of trees, right? And that turns it into a probability. Agreed?
Yeah.
So what you would have in a discrete probability distribution, and in the context of our example, you would have probability as a function of the random variable x. Okay? Here you'd have the random variable x. In our case, it is, what did we say? Tree height. Okay? And let's, for argument's sake, let's do one of these. Let's, for argument's sake, say, let's say we, oh, it's going to be annoying. instead of doing 1,000 trees, let's make life easier. Let's let there be 10 trees, okay? Let n equal 10, okay? So we have 10 trees. So, and let's measure it in centimeters. So let's say we had here 100, let's say 150, 200, 250. We shouldn't do this in centimeters. We should do this in meters to make it more realistic. Let's make this a meter. Let's make this 1.5 meters. Seems a little silly. 2 meters. Let's say we have very short trees, just for the sake of me not having to draw so much. 1, 2, 3, 4, 5, 6. Let's put 1 here. So let's say that we have 3, we have 4. Now, let's say this here is, let's say, 1 over 10. So we have about there. So that's 2 over 10. We have about there. One here. Let's say we have one here. Say we have one right in here. So far we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These should all be roughly at the same height, right? If you add up all the probabilities, do you get 10 out of 10? 1, 2, 3, 4, 5, 6, 7, 8 plus 2 is 10. Okay. So this is what's called a discrete probability distribution. Okay. Now, we'll deal with continuous probability distributions later as well. If we wanted to talk about the average tree height, thus far in the course, we've defined average, let's say for the population, as the sum from, let's say, I is equal to 1 to n of all of the actual tree heights. This is my random variable x. Random variable. Okay? And in our particular case, that would correspond to, I don't know what the actual numbers are. They're pretty disgusting, but I'll write it out generally. x1 plus x2 plus dot 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 plus xn all over capital N. But are you guys with me so far? You guys following this so far? But there's another way of defining average, which, yes, go. You okay? What's wrong? Okay. There's another way of defining average, which statisticians use a lot for various reasons, and that is expected value. So this means average, right? This means population average. Yeah, well, why is it not a sample average? Why is this a population average?
You're using option.
I used all of them. But there's another way to define average. And the word that is used is expected value. So E stands for expected value. So the expected value of the random variable x means the average of the random variable x. And it's defined a little bit differently. It's defined using this formula.
Not you.
N in this particular question is how, in this formula over here, how big is n? Capital N.
10.
In this formula though, capital N is only going to be equal to 9.
Why is it equal?
Because when you define average using the expected value formula for a discrete probability distribution, the total number of data points that exist, or rather the total number of values that exist within the formula correspond to the number of unique values of the domain. In this case, x2 and x3, here, x2 and x3 equal the same thing, let's say, right? Agreed? They're both 1.5 centimeters, no, meters, right? But in this definition of average, 1.5 doesn't exist twice. It does exist twice in the context of this, which is going to be the probability of it, the 2 over 10, or what they'll call probability mass function or probability density. But it won't exist multiple times as a value of x pi. How many of you guys sort of understand what I'm saying? So in other words, in this particular case, what you have is the sum from 1 to 9 of the following. 1 over 10 times x1 plus 2 over 10 times x2 plus 1 over 10 times x3 plus 1 over 10 times x4 plus 1 over 10 times x5 plus 1 over 10 times x6 plus 1 over 10 times x7.
So is it kind of like the weighted average?
That's exactly what it is. But weighted average
Yeah.
is a subset equation of average.
Subset equation of average. So,
If you take a look at this, how many of you guys see that this is actually the exact same equation as this?
I see it.
Because this point, right? What is the common denominator for each term? 10. What is the denominator here?
10.
10. The only difference is when it comes to data points x2 and x3, they exist separately. But here, data points x2 and x3 are clumped together as a 2 over 10. Do you see that you could split this term into a 1 over 10 plus a 1 over 10? 1 over 10 and 1 over 10 equals 2 over 10. Okay? So it actually does equal the same thing. It's a different way of defining things. You associate a weight or a probability mass with each of the different possible values of the random variable x. So in this particular case, as I said, that corresponds to the different or unique values of x. You understand? Yeah.
So if it's the same thing, why does that exist? What is the use for?
This particular notation is quite useful in terms of developing other formulas. Okay? For example, the sample standard deviation formula, which has an n-1 in the denominator, is not the easiest proof to show. And one of the ways to show it is through the use of expected value, as well as other things. Because in order to show that proof, you have to do a little bit of manipulation of things. And expected value has particular properties associated with it, which you develop and you prove, like, you know, distributive property, pulling out constants, and so on and so forth. And once you develop those rules, you can then go ahead and use that notation to do a lot of things in a more efficient way than that. Yeah.
Question. So the capital N equals to 9. However, the equation you plus it to 10.
Shouldn't.
Is that a problem?
Yeah, of course it's a problem. It's wrong. What should happen here?
It should be 9.
That's right. Oh. That's right. Okay.
Yeah, I think it comes back on
Okay. Any questions on that so far? So, expected value really is the heights or the y-coordinates of each of these data points. Every data point here is, this data point has a value 1.5 comma 0.2, doesn't it? Because 2 over 10 is 0.2, right? So expected value really is each of the x, it's the multiplication of the x and y coordinates of each of these data points, isn't it? Summed up. You see that? I repeat, expected value in relationship to this particular graph is the sum of the multiplication of the x and y coordinate of each of these data points. Right?
Write it on the board.
Yeah. Expected value equals the sum of multiplication of x and y coordinates of each data point in the set. So this would be 1 times 1 over 10 plus 1.5, sorry, yeah, this would be 1 times 1 over 10 plus 1.5 times 2 over 10 plus 2 times 1 over 10, and so on and so forth. Okay? All right. Now, as far as this course goes, expected value comes up again a little bit later, but not to a good extent, but it doesn't go ahead, or rather it's not my responsibility to teach you expected value laws and so on and so forth. I could, but I don't think you guys really care. Those of you that care about math will learn about it later on. If you are interested in understanding why the denominator for sample standard deviation is n-1 as opposed to n, we can have that conversation and I can take you through it, and we can talk about estimators and all of that stuff. Okay? But for now, I'll leave this at that. If we were to talk about a uniform probability distribution, that would simply mean that, of course, all the data points would be flat, right? Uniform probability distribution is one where the frequency of each of the possible values of the random variable x is the same. Okay? Now moving on, there are particular discrete probability distributions that they want you to be familiar with in this course, and the development of them will be easy for us because they're based on combinatorics knowledge that you already have. So it's simply a matter of me introducing each of these distributions. I think there are only 3 that they want you to know about, for us to generate the general formulas for them, which you'll understand because you have the knowledge to. and then for you to start answering questions about them. And the first one will be a binomial probability distribution. So you need to recall that what is a binomial scenario? What is a binomial situation? Put up your hand. If a problem or a scenario is binomial, Naomi, what does that mean about the problem? If you are painting a house and your options for paint are binomial, how many color options do you have? 2 color options, right? Would flipping a coin be, would the options for flipping a coin be binomial?
How many coins?
Yeah. Okay. Now, because you can have heads or tails. Now, what's interesting is, I could ask you, options for rolling a die, are those binomial? No, there are 6 options. However, if you define a problem in terms of 2 options, meaning succeeding or failing, then a problem is binomial, right? If you have success, if you only have success or only have failure as outcomes for a problem, then that problem is binomial in nature, right? Unlike the Olympics where you have, let's say, bronze, silver, gold. That's a trinomial problem. But if you create a scenario where the only options or outcomes are defined as success or failure, then the problem is binomial. And then, based on the definition of things, the internals can have multiple options. So if you define success by rolling a die as getting an even number, even though you have more than one option, which are more than 2 options which are even, the overall possibilities for the event are either success or fail, which is binomial. Okay? And so there's a formula, a general formula that exists for a binomial probability distribution. This is discrete. Okay.
Are we going to learn non-discrete?
Sorry?
Are we going to learn non-discrete?
Yeah. And I'm probably missing an n choose x here. Do that. Stop. So, lowercase p is going to be defined as probability of success. And what do you think lowercase q is going to be defined as?
Probability of failure.
Probability of failure. And that's why in the equation you see q is replaceable with 100% minus p. Now we have to talk about the rest of the equation and if it makes sense. Now let's talk about it in the context of a question. And in the context of a question, I think the equation will make more sense.
It's like the binomial triangle.
You don't need it. That's it right there.
The probability distribution for the number of 2.
What is the probability distribution for the number of 2s resulting from 4 rolls of a die? Okay, so in the previous, when the board was up, before I erased the board, the probability distribution that I gave you was graphical, okay, or a sketch. Does a probability distribution necessarily have to be shown, do you think, as a sketch? What's another way you could show it? A table, right? Table of values, your x and your y data, right? So if I ask for a probability distribution, it doesn't mean that you have to sketch it. In fact, if I ask for it and I don't ask for a sketch, I prefer that you just give it to me as a table. Easier for you, easier for me to mark. Okay? So, in this particular problem, we're going to define P as getting a 2 on a single roll. Okay? Now what is Q going to be? Not getting a 2 on a single roll. Right? I need chalk. Chris, give me a piece of chalk.
Sir, you can't find any because you borrow a lot of.
So I have a question.
Yeah.
How does every other teacher get chalk?
Well, most other teachers teach in one classroom, maybe 2. I teach in 3 classrooms that are all over the place.
And I know, but how do they get chalk?
Oh, you go down to the
main
office. They'll give you a box of chalk or something. But for me to carry calculators and chalk and all this, it's just not practical.
But Miss Benaki never runs out of chalks.
She probably hides it somewhere.
Yeah, I think so.
So,
She takes it with her.
something that's very important to note about a binomial probability distribution. Oh wow, who'd you go to? Next door. Nicely done. Something very important to note about a binomial probability distribution, and that'll become evident, or that should become self-evident when you think about this particular question, is that n, okay, which refers to the number of trials, if you will, number of trials. Let me repeat that sentence. Let me backtrack for a second. I'll just write this down. So, the critical aspect of binomial probability distribution has to do with the trials. In this particular question, what is the event? And let's say number of trials of the defined event. What is an event in this particular question? What is an event?
rolling a die.
Yes. Rolling a single die and reading the result, right? When event 1 is completed, Gehrman, does its result have any bearing on probability for event 2?
Yes, it does.
Really?
No, I don't know.
If I roll a 2 for event 1, does that have any bearing on my likelihood for success for event 2? What if I rolled a 3?
You can get the same results like many other.
So what that means is, what's critical to know about a binomial probability distribution is that the events are independent that's not good to say. It's the trials, right? It's the trials. The trials are independent from one another. And therefore, P is a constant. And Q is a constant. Because P is the probability of success per trial, probability of rolling a 2, right? And so Naomi, whether you rolled a 2 or didn't roll a 2 on your first trial, does that affect the probability of rolling a 2 on your next trial? No. What's the probability of rolling a 2 going to be for each roll, Naomi? And what is that value going to be? Yeah, 1 out of 6. So for our particular question, we can say that our probability distribution will be generated from the formula 6, choose x. Well, I'll write it in the same order I wrote it over there. 1 out of 6 to the x times 5 out of 6 to the 6 minus x times, for some reason, 6 choose x. That's right.
What do you mean by for some reason?
Well, we're going to discuss. You guys are going to tell me, based on your knowledge of the course, why that is the correct formula.
Why that is the correct formula?
Or if it's the correct formula.
6 choose
How many rolls are there?
4.
So then what am I doing here? Should this be 4?
Yeah.
And should this be 4?
And then what about the 5 over 6? Would that be a 3 then? Or?
What is P going to equal? What's the probability of rolling a 2, as Naomi said?
Oh, okay.
And what's the probability of not rolling a 2 for a single trial?
Oh, okay.
Okay. A single. Okay. Now, how many trials are there?
4.
4. Okay. If you, I'm not saying that you have to do this at all, but just for this explanatory phase, your denominator is always, what is the, if you were to break this up in terms of numerator and denominator, this is going to be interesting. What does the denominator look like?
6 to the...
Funny, I've taught this so many times and now I'm thinking. It's going to be 6 to the 4, isn't it? Right? Well, let's say this is 1. Let's say this is 1. How many 6s do you have down here? 1. And let's say this is, then that has to be a 1. You have 3, right? You understand that your denominator will always have 4 6s in it? Doesn't matter if x is 0 here, and this is 0 here, you don't have any 6s from this one, you have 4 6s from that one, right? You see that? So, if you have 4 6s, that means your denominator is always going to be 6 to the 4, which is 6 by 6 by 6 by 6. Interesting. So that is counting, that tree, that tree which is going to have 6 branches, and then 6 branches off of each of it, and each of it. It counts order, right? It counts the total different number of ways that you can actually get a result of 4 rolls, right? With the same die over and over and over again. Numerator is also going to count order. Agreed? Okay?
So they're gonna...
Now, that's fine. But there is one other aspect to the equation. That 4 choose x. Do we need it?
It wouldn't be there if you didn't need it.
So then think about why you need it.
Because, sir,
Yeah.
isn't there like, wherever we do, wherever we roll the die, so, never mind.
Oh.
Never mind.
No, I think 4 choose 1 is there because of the...
If you were to expand the numerator here, right? If you were to expand the numerator here, notice, I would almost think of this as 6, 6, 6, 6, x, 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 x. And my numerator, let's say, is going to be 1, and it can happen any certain number of times. We can call it variable y. Y is a subset of x, and then the 5 is going to exist. Let's say this happened once, for example. This is going to be the probability of one success, 5 by 5 by 5. Now, what is y? Y is getting a 2, right? X is anything from 1 to 6, right? And Z is 1, 3, 4, 5, or 6, right? If you look at this particular tree up here, right? The first stage of this tree counts success, right? And then after success, it does allow for jumbled up orders of the failures, right? So the way this equation is written, it's saying success happens first, and then you can have any combination of failure in any order afterwards. But does this question say anything about caring about on which roll a particular number of successes happens? That is to say, if we are to calculate, oh, and I'm missing something in here, by the way, because what could happen? You could have no successes, right? Let's say we were to calculate option x equals 1. That corresponds to one out of your 4 rolls coming up as a 2. This probability over here gives you the answer for the first roll coming up as a 2 and the other 3 rolls not coming up as a 2. Who sees that based on the variables? But the question doesn't talk about only having the first roll being a success. It just cares about the fact that any one of the 4 rolls are a success, correct? So you could have success on roll 1, and failure on rolls 2 to 4, success on roll 2 and 3 failures, success on roll 3, or success on roll 4. Agreed? And each of those events are mutually exclusive. That is to say, you cannot have only your first roll come up as a 2 and the other ones not come up as a 2, and at the same time have your 4th roll come up as a 2 and have the other ones not come up as a 2. So guess what you have to do with each of those cases? You multiply them or you add them? What do you do with events that cannot simultaneously exist?
Multiply.
Add them.
You add, right? If I can only wear one shirt, if the rules of the game say I can only wear one shirt, the gray shirt or the red shirt, probability of, and let's say there are 3 colors, gray, red, and blue. What's the probability of getting a gray? What's the probability of getting a red? What's the probability that I can be wearing a red or a gray shirt? 2 out of 3. You did 1 plus 3 plus 1 plus 3. So here, for example, in the case of having one success, you could have success on roll 1 or on roll 4. And the probability of success associated with each of those cases is this. So what do you have to multiply this by?
4 choose 1.
4 choose 1. 4 rolls whereby you choose one of those rolls to be a success, right? Now, if you're talking about the case of having 2 successes, right? That means you have 2 of the 4 events being identical, right? And the other 2 being identical because they're going to be failures, right? But in terms of success, you would have 4 factorial, right? You have 4 choose 2, right? Whereby only 2 of the 4 events are going to come out as successes. Does that make sense? And do you follow that? So then if we follow the formula here, in this case we have,
Good morning.
oh, the attendance. I will bring it to you, is that okay?
That's perfect. Thank you.
So,
So you break the rule again.
I know, I broke the rule. So if we talk about this particular case, I know you're going to say it's silly to write it, but I'll do it the first time just to show you the equation. You have 1 over 6 to the 0, right? You have no successes. You have all failures, which means 5 over 6 to the 4 minus 0, right? Times 4, choose 0. What's beautiful about this is, and it goes really nicely with the tree, is what you end up with is just 5 over 6 to the 4, right? Now, what's nice about that is, do you guys agree with that so far?
Yeah.
If you go back to the tree for this particular case, I erase the 1, and what do I put here? I put a 5 and it's a Z. Notice, all possible orders, all possible orders. All of the order is taken into account here. All possible orders for 4 rows in the numerator, all possible orders for 4 rows in the denominator. There's no need to multiply by anything there. Okay?
Wait.
Yeah.
Okay, so under the case before that, when we had 1 success.
We're going to do it right now.
No, but I have a question.
Yeah. So let's do 1 success now. 1 over 6 to the 1. 5 over 6 to the 3. 4 choose 1. And we have, I don't want to do it. I'm just going to write it like this. 1 over 6, 5 over 6 cubed times 4. I'm just going to leave it like that. Yes?
Okay, so up there we have 1, 1, and then 3, 5.
And I'm going to call this a y.
Okay, and then we have multiplied by 4.
Mm-hmm.
That 4 will put the success between all of them, all the possible ways, right?
See, the problem with this is, and this is where I was trying to explain to Mr. Gao, you know that hard question that we were doing? That crazy question? Probability is very tricky because, yeah, you can multiply probabilities of events that can coexist, whether they're dependent or not, right? Like if I want to know the probability of drawing 2 aces from a standard deck with replacement, it's going to be 4 out of 52 times 4 out of 52. If I want to know the probability of drawing 2 aces from a standard deck without replacement, it's going to be 4 out of 52 times 3 out of 51, right? In both cases, you're allowed to multiply. But in both of those examples, whether you're dealing about with, or if you're talking about the with replacement case, you have a 4 times a 4 divided by a 52 times a 52. You have, let's say, a z times a z over an x times an x. All possible orders for all stages divided by all possible orders for all stages. When you do something like this, you have trouble. And the reason why is, this is injecting order for all 4 stages. Does this inject order for all 4 stages? No, it only injects order for the last 3 stages. You see? Like if you draw your tree, it's just going to go, that tree goes like this. 1 possible success, right, which is getting a 2, right? And then it's going to have 1, 2, 3, 4, 5, and then it's going to have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then one more time, right? 5 off of each of those. What the bottom 3, sorry, 1, yeah, and then you have it again. You see that you could end up with, in the last 3 stages, you could end up with, let's say, 4, 1, 4, 3, for example. But you could also follow a pattern which will go 1, 4, 3. Agreed? So the problem with that is that it's counting order, but it's only counting order for the last 3 stages. But your denominator always counts order for all 4 stages. So you have to inject order of success across how many stages? 4 stages.
Oh, so you add 1 stage.
See, by doing it this way, right, you don't have order across all of the stages. You only have order across the 3 stages. But nothing says that you can't succeed at stage 2, 3, or 4. Right? So you gotta, yeah, exactly. So you gotta jumble it up. Now, if I asked you, what's the probability of you, if I asked you, what is the probability that you roll a 2 on your first roll? Your answer is this. Sorry. Yeah, this one right here, right? You understand if I asked you, what's the probability that you roll a 2 on the first roll? You get rid of the 4C1, that's gone.
But then you're going to get rid of the order of those as well.
No.
Wow.
Because you want to allow for any possible order for the... remember, it's all about equally likely physically possible outcomes. If the criteria is rolling a 2 on your first roll, there's only one way to do that. But let's say your next 3 rolls come out to be 6, 4, 6. There are multiple orders in which you could get 6, 4, 6 on the last 3 rolls, all of which, following a roll of 2 on your first roll, still count as a success. So you have to allow for those possibilities. Otherwise, you're undercutting your answer. Right? It's hard. This stuff's tricky. It's easy when you just like look at the formula and you just do it. But if you really want to think about it, it's a little trickier. But it's fine. So if you just follow along, now that you believe it, we could just follow along. This would be 1 over 6 squared. This would be 5 over 6 to the it always adds up to 4, right? 4 choose 2. This one's going to be 1 over 6 to the 3, 5 over 6 to the 1, 4 choose 3, and then you're back to the opposite of the other one. 5 choose 6 to the 4, 4 choose 4. You crunch those probabilities.
Last one is wrong, sir.
Last one is wrong.
1 over 6 to the 4. You did the same.
Oh, I'm going back to the beginning. Yeah, that's got to be that. That's got to be that. And what are does somebody know what the numbers are? Maybe give me them to the nearest 100. Do you guys understand that, I'll make a note here, if this is just for knowledge, where y and z are subsets of x, shoot, when I draw x's here, you know I don't mean that x. You know I don't mean that x, right? Here, I can call this
You just want the
T here, T, 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 T. So it's like, this is T, and what lives inside are
Bunch of 6.
Y and Z.
Oh, why?
Y, and this is Z.
Why?
Because this corresponded to which case? This corresponded to this case, right? What is Y? Getting a number 2. What is Z? Getting
not
1, 3, 4, 5, 6, right?
But shouldn't Y and Z cover the whole thing?
They do. They do. If you want, I guess I could have drawn it like.
You could have just like.
I could have drawn it like
You could
that.
have drawn a circle and then divided it into 2 parts.
Yeah, you could do that. Here, I'll go nothing here. You get the idea, right? That's just doing a visual of what we talked about there. So, do you guys have the numbers there? Just curious. Of course, what should all those numbers add to?
1.
Yeah, or 100%. So, can somebody just give me those and we'll call it a day?
Come on, Ken.
Most people don't think about this part. They just think about, I have a 1 over 6 and I have a 5 over 6 to the 3, and I have 3 events that are the same and 1 that are different, and then I multiply by 4 factorial divided by 3 factorial, which is 4 choose 1, right? But that is a dangerous way to think about things. It'll get you into trouble, particularly in those difficult questions like that question with the odd and even thing, the game show. By the way, I forgot, I'll give you a photocopy of the answer as well, and a little write-up about this too.
Sir, the last
I made a little paper.
Sure.
Yeah, I know, I never give you this stuff. I know, I'll give you
The last one.
Okay, just give me the numbers.
The last one is 7.71 multiplied by 10 to the power negative 4.
Oh, yeah.
Yeah.
These are just details, but.
Okay, so the second last one is 0.015.
over 216.
Good enough, whatever.
125 over 324.
What? So the third last one is 4.822 multiplied by 10 to the power negative 3.
Okay, you guys are. You know what I would like? give me them all as percentages to the nearest. So like, give me everything as a percentage to the nearest
Okay, the third
100.
one.
Give me the first. Give me the first.
But I already have the third one.
Okay, give me the third one.
0.48.
That's a percentage, or is that?
It's
So
a
you-
percentage, 0.48%.
Okay.
It's really small.
You don't mean 48%.
No, I don't.
Okay, go ahead. What else? Now, with a graphing calculator, you could do this a lot
The
faster.
last one is 0.077. Really small.
I'm assuming the first one is going to be very big. Otherwise, we're not going to add up to 100.
Yeah.
No, it's not 100.
It adds up to 100?
Oh, the fourth one is 1.54.
Two more. You got a lot of ground to make up there. What's 5 over 6 to the 4? Let's go 5 in brackets. 5 over 6 to the 4. Should be big. Better than you.
Is
48.
what? Point? 0.48. 5 over 6 to the power of 4 is 0.48. And
So
then-
it's 48%.
Yeah.
So what's this?
Okay, it's
I think you made, yeah, we go on, what's this? What's the second one?
just a second, just a second.
39%.
39?
Yeah, actually it's 38.58.
So, was this 48 clean?
48.22.
This is 48.22. This is 39 point what?
No, 38.58.
58.
Does that add up?
No,
That doesn't add up.
It does.
no, it doesn't.
It does.
It does not, even close.
It does.
No,
What are you talking about?
Yeah,
Not even close. Something's wrong.
I did the second one, like
The third one is wrong? What do you get for the third one?
0.69.
Oh, true, the third one.
0.69? As a percentage, I mean.
169.
That's not going to make a difference for us.
Sir, I got 11% for the third one.
Really?
11.57.
Really? Another?
It sounds a little bit better here. 70, 86, 96, 97, 90. I think that's closer. That might be it. Yeah? That looks closer to 100 to me.
But I keep giving 0.48.
But
That,
for which one?
Oh! Nothing. Never mind.
Your calculator has a problem. It's made in Persian. It's made in Persian. Sir, it's
It's
11.
7.7.
It's 11.57 is right. The third one's right.
What am I getting?
Because your calculator is made in Persian. That's the only problem.
You see the staples.
Okay, is that good enough for today?
It's China.
Is that good enough for
Why
today?
do I keep getting 7.7?
Because it's made in Persian.
Drop the short. 5.
It's 11.57.
Oh Lord! Don't say 57. English is a stupid language. For some reason, after the decimal, you have to just quote the numbers by one. So you say 11.57. Just get used to it. That's English. So if you have a number like 11.123, don't say 11.123.